Hello, everybody. So today we'll talk about the old exam, and we'll go through that step by step. And I hope I can clarify some questions here. And then, of course, we can talk a little bit about the old exam. Interesting. I do not move the mouse at all. Like there's some ghost in here. Okay. So you get the exam. Like I think I will do the structure for a new exam exactly like it is here. I simply will change the questions a little bit. So that's at least my idea. So yeah, how much current does a typical microcontroller pin provide?
I mean, few milliamperes.
Okay, where do you have this information from?
Is in the material?
Experience?
No, not really, because if you look closely, everything I asked there was in the slides. Yeah, so it is here, and simply you can see the range down here. Okay.
Yeah.
So a few milliamps. All right. Typical supply voltages. Okay, this one wasn't in the slides, but we discussed that extensively.
Yes.
Yeah. So what's the answer here?
It's 5 volt.
5 volt. Okay.
3.3
and 3.3. Okay.
and 1.
Not really. The thing is, I knew that 1.8 is arising, but it's not really a standard yet, and therefore I decided to go for 1.0, which is not there.
Okay.
So, but again, you might want to look simply into that small table here. So what is stored on the stack? And maybe you want to localize the stack again and talk a little bit about what the stack is doing. Here we are. So now we have our CPU, the bus connecting all the bits and pieces of our microcontroller, and then there's the RAM with the dynamic memory in here. So on there, one part of the RAM is the stack. Okay, and I mean, like, yeah, there's already the explanation here, but how does this work again? I want to focus a little bit on the stack here. So how does this work with the stack? Well, if you, for example, let's say we do have an main function, okay? And maybe in here, let's say I do have another function which I call add two numbers. And I say in here maybe C equals A plus B, and I want to return C, okay? And then in here, I say, maybe I want to have okay, and maybe I have something like that, okay? Like this variable now is not used, but I think that should be clear. If we now have such a software here, then all the variables, they require memory. And now the question is where this variable is stored. So for example, if we do have a global variable, which is basically present all the time, no matter if you are in a function, it is always present. So it's a global variable, and we'll go to this global variables section, okay? So however, but if you are now in your function in here, yeah, for example, in the main, or you jump into, there is the type missing, or you jump into a function, then suddenly you require more memory, because in this function here, you do need an additional variable C. okay? And this variable has to be stored somewhere. And all those variables which are required within functions like this or like that, doesn't matter, they go to the stack, okay? Now.
So basically stacks provide additional memory.
Yes, yes. But the thing here is that now imagine, and maybe down here we do something like a print or blah, 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 whatever, some code. Then the interesting thing is that if we are in this function now, we need additional memory. But once we leave this function, we do not need this memory anymore. This variable doesn't exist anymore. So what the stack is doing, and that's why the name is stack, like it's stacked memory, okay? Now we don't need it anymore, so it's unstacking the memory. So it's like a pile which is all the time going up and down. Okay, is that understandable? That's important.
Yeah.
No? Now, we can do nasty things. So, and this is also, or we will see that. We will see that in a second here. Like there are more stack questions to come. Okay, but for now, what is stored on the stack, those are the local variables, okay? And local variables are the ones which are defined within functions, okay? This is a global variable. This is basically accessible from everywhere all the time. Those variables, they are only accessible within a function. They are local variables, okay? And they are stored on the stack.
How about static variables?
Okay, very good question. If you do have a static variable, static, where? If you do have a static global variable, now this is like nothing you need to learn for the exam, but I just want to answer that. If you use static in here, then this means that this global variable can only be accessed within this file. This is what static means for global variables. If you do have a static in here, then this means something else. Then this means if we use this function again, then the old value will be preserved. Okay, so it's not like, I mean, like in this example now, this doesn't make sense, but we could say plus D, and D maybe is C, something like that. Then basically, once we have written to that, the next time we call that function, the value still will be in here. Yeah. However, in that particular case, that static variable also is a global variable.
Okay.
Yeah. But as I said, now this is nothing for the exam. This is now special knowledge about the programming language. Okay. Is it better to use lookup tables for mathematical functions instead of computation of the result for every request?
It depends on the requirements.
Mm-hmm.
Yeah.
So let's open that again. That was too far. Where was that stuff? Here. Okay. So, whoops. We can either calculate the result, or we do have a table with pre-calculated results. Okay. So the question you have to ask yourself is like, for example, how often is this called? Yeah. So because the more often it is called, the more processing power it consumes. Also, do you want to have the result fast? Because this will take some time for the computation. Here, you simply jump to some point in memory. Yeah. So, and I mean, like those, and of course, if you do have a lookup table, then you consume a lot of memory. Okay. So, typical question: do we want to be fast? Then, for example, we need a lot of memory. Is it okay to be slower? Then we need computation power. Yeah. So, but for this question here, It always depends on the constraints and the requirements of the application. You cannot answer like one is better than the other. Okay. Yeah, which communication protocols are suitable? I mean, like that, for example, is a lookup question. Because I've mentioned that simply in here. So you can look that up. Basically, where I wanted to go with that, or why I also gave that other examples, those communication protocols, they are very easy, okay? They are really on the bit level. While if you do have something like USB, Bluetooth, or Ethernet, maybe at some point in your life you looked into that, that's a pain in the ass, okay? Like those are really complex protocols. And but if you say, I just want to have a small humidity sensor, okay, then of course this humidity sensor doesn't come with an Ethernet stack. Yeah, but instead you really have those low-level protocols here. Yeah? Maybe something for the exam, if I think about new questions, then have we looked into that? Have we looked into how that works? Not really, so I cannot ask that. Okay. Yeah, because here, oopsala, because in here, maybe I should close that too. What you do with I2C and SPI is basically you really give just like the memory address you want to read or write, and then you read or write from that memory address. That's it. And that's what those protocols are doing. But we have not done this in here. Oh, the pointers, the pointers, the pointers.
Professor, just so the previous question is I2C and SPI.
Yeah.
So if like for the exam sake, you actually choose one. If I remember, I can remember I actually chose the SPI. So
yeah,
it's a +1 -1.
-1. So it's plus.
I didn't choose the wrong answer.
Or for no answer. No, I think no. In that case, you got 1 point. Yes. And then 2 would had been possible. So, but you got 1. Then, if you just ticked 1. If you would have, for example, also ticked USB, then you would receive 0 for that question. But multiple answers can be correct. No?
Yeah, and I have a question.
Yeah.
I2C is a one-way communication and SPI is a two-way communication.
Not really, not really, not really. They are both master-slave communications. Yeah, master-slave, master-slave. So you are right. Basically, the master is controlling like in which direction. So this is here, for example, it's half duplex. Okay, so the master decides if he wants to write to a slave or if he wants to read from a slave. Okay, here it actually can be full duplex because you have a line master out, slave in, and master in, slave out. Yeah, so two-way here. But also here, the master, as for I2C, the master has to provide the clock.
Yeah, I thought it's a small humidity sensor, so it will just one-way communication and it sends the data. So I thought then I only take I2C.
I'll show you. I'll show you. Thing is, let's say maybe let's take this other fruit thingy here. Yeah, that fucker. Sorry, but if we documents datasheet, digital interface, so we can see how the protocol looks like, and at some point there should be a register map. Where is it? Here we are. So basically what you can see in here is like all the registers that thing has. Yeah. So, and I can tell you, and this is such a pain, that before you can read the humidity out of that stupid sensor, there is so much stuff to do that it is better to download the software from Bosch and simply use it, though nobody has any idea what this is doing. Yeah, because you need to configure everything in here. You need to calibrate the humidity, whatever this means. I don't know. Yeah. So you really have to write stuff into here before you can use that device. So in fact, it has to be bidirectional, because otherwise you couldn't configure your humidity sensor or whatever. No? So this is typically, I'm just thinking about if there is a thing where it's just one way. I don't think I have ever seen that. It's always two-way, because you always need to configure that. Even if you have a TFT or something, like what's the orientation, what's your desired speed, blah, 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 blah. Yeah. Because what manufacturers are doing, what's happening really in there, those devices are damn stupid, okay? And they do not have internal logic. So instead, what they say, the microcontroller attached to it will handle all the logic, so we do not need to integrate that into our device and can sell them cheaper. Yeah, so that's a little bit how this is working.
Okay.
Okay, pointers. Whoop whoop. Still a bit of problems with that, huh? Here we are. So, which statements about pointers in C are true?
There are variables that contain an address.
Exactly, because if we look here, we created a pointer p-test. So there's some machining going on outside. If it's too loud, let me know then so I can close the window. So we have a pointer p-test, okay? And as we can see in here, it also requires memory. And in this memory, the address where we want to point to, so the address of test, this one, is stored in here. So that is correct. How about this one?
They require memory.
They do require memory, okay. So does their size change with the data type they're pointing to?
Yes.
No, because they are saying just address, and address is
exactly. Address is address. It doesn't matter what kind of information is stored at this address, but the address is the address. It's always the same. Okay? So their size will not change with the data type they're pointing to. Okay? Good. Free text, no need to fill. What is the Stack Overflow? Yeah, that's what I meant when we talked about the stack. Can open that again. What the heck is a Stack Overflow?
And when the stack is filled more than its stack capacity?
Exactly. So imagine the following. How could I do that? For example, in here, I would do a so-called recursive call. Yeah. So if I'm in here, then I require new memory. Then I jump into that same function again, require more memory. And I mean, like I can go on and on like that forever. The problem now is that every time I enter that function, I need a little bit more memory. Okay. And at some point, there is no memory left. And now it depends a little bit on the system. Some systems do have protection mechanisms and they can simply detect that. Especially for microcontrollers, very often such mechanisms are not in place. And what will happen then is that you basically consume memory which doesn't belong to your application. Yeah. So for example, you suddenly, it depends on if the stack grows from top to bottom, then you might want to overwrite the data that is stored in the heap. Yeah. Or if it is bottom up, then you at some point might override global variables. And then, of course, your system can do very crazy things if suddenly variables do hold a wrong value, okay? This can happen for so-called recursive calls, as it is in here. But of course, this could also happen if I say in here, yeah, so of course, I do need this array here, which I call text, and in there I need at least, you know, that number. Yeah, that's what I need. Yeah. Of course, if you do something like that, so like you require a lot of memory in here, then of course, again, the stack might overflow. So what can lead to stack overflows? Like 2 examples.
Loss of elements in the memory.
No, but what in code, what could you do? Like, let's say, for example, you want to have a Stack Overflow on your own, yeah, or you want to provoke that, or what should you avoid in your code so that a Stack Overflow does not happen?
Dynamic memory.
If we didn't clear the memory after using variables.
No, but I mean in here,
yeah.
like for example, now I made this, yeah, and this might cause a Stack Overflow. Okay, so how could we describe what I've done there? So basically in here, what I did is I used a big data structure now as a local variable. So basically, so if you would like to write that down, you use big data types as local variables. Yeah, that could be one thing. Another thing that could cause Stack Overflow might be, for example, a so-called recursive call. Okay, so we invoke the same or call the same function over and over again, and every time we need a little more memory, and at some point no memory is left. Shall we repeat that?
Yeah, the first one.
Yeah. So general idea is we do have a piece of memory in which local variables are stored. And of course, this piece of memory has a limited size. Okay. So what goes in there? Basically all the local variables. So variables which are declared within a function. Okay. Now, what could cause a Stack Overflow? One reason might be you have a function which needs certain stack. So in that case, this one integer variable. And if I now call this function again, then of course this again will require some memory. But this function again will call itself to require more memory. So, and if this continues forever and over again, at some point you will run out of memory. Okay, and this running out of memory is called a Stack Overflow. That could be one cause. Another cause could be to use big data structures. So something like that.
So big data structure means it is requiring more memory than which is available on stack.
Exactly. Yeah. So for example, if I say for my print, I want to have a storage in which I store my text. Yeah. So I could say maybe, oops. And then I use something like that, yeah, at some point. However, the problem is that in here now I used up nearly 1 kilobyte of RAM because I declared this variable which is very big. No? And I mean, like I think you had SDHD. I saw some students who put the value buffer for the ADC within the main. Okay, so, and of course, if you put it in there and not in global variables, then this caused, in their case, caused the stack overflow. Yeah, because they put this big piece of variable inside of the stack. Yeah, and the stack isn't that big. Okay.
Okay.
Like, tell me if I should repeat something of that.
No, it's clear.
Okay, good.
So majorly, we have two major points that can lead to stack overflow.
Yes.
Like the summary here.
Yeah, and they are?
You say using big data types and the local variable, and also recursive call.
What was the second?
Recursive call.
Recursive call, yes, exactly. Good. Or basically recursion. Yeah, that's like, you can abstract that a little bit. What if it's the principal problem of precision with floating point numbers? So I did not really mean like those here, but any floating point numbers. The principal problem. Any idea? Well, the problem is how many possible numbers exist between 0 and 1?
Infinite.
Infinite, okay. How many possible numbers can we represent with 32 bits? 2 to the power of 32. Okay. Let's say even if I do have a gigabyte of RAM and I use up that entire gigabyte of RAM just to represent a single number, that maybe is 2 to the power of 1 billion, which gives us an incredibly huge number, but it is not infinite. Yeah. So even if we would put all the memory and processing power we do have on the entire planet, we will still not be able to represent every number. Yeah, that's unfortunately a fact. Okay. So the principal problem here is that we try to describe an infinitely precise number within finite system. Yeah. So there will always be imprecision. Of course, that might be incredibly small, or maybe you have workarounds. For example, you can work with fractions and stuff like that. Yeah. But still, like, this is the principal problem. Principal problem, we try to represent an infinite value with a finite representation. Okay. That's clear?
Yes.
Okay. Name and explain one problem with dynamic memory allocation on embedded systems. Just one? There are so many.
Memory management.
Hmm?
Memory management.
Yeah. So what does this mean? What's the problem with that?
Like with time, the memory becomes fragmented.
Uh-huh. Okay. Okay, yes. Yeah, sure. Why not? Okay. So memory can get fragmented. Okay, and what's the consequence if it gets fragmented? Then, for example, in that case, we could not use the entire memory. Yeah. Let's say it's heavily fragmented, and I request new data which does not fit in some of the gaps, then I'm screwed. Okay, yeah, because then I can't find a piece which is big enough. So fragmentation could be one issue. Okay.
But I didn't understand what it means, fragmentation.
Okay. Let's imagine that this is our heap. Okay. So, and I'm the Excel pro. So, and let's say, so this is our entire memory, okay? Then the application in the beginning maybe starts, I need 16 byte, okay? So 16 byte go to application 1. Okay, then the next application says, I need this number of memory, okay? So this goes to that other function or whatever. Now this function says, no, I don't need that memory anymore. Now the next call comes and it needs maybe this piece of memory. So suddenly what's happening in here is that gaps start to form. And even though in theory we have this number plus this number of memory free, we cannot use it as an entire block because it's two pieces. It's fragmented. Okay, shall I maybe come again what a stack is doing or like how this works? Or was that already clear?
Yeah, it's clear.
It's clear?
Yeah.
Good. Yeah. So, and you might, for example, yeah, it's still there. So there is this Windows tool, this defragmentation, blah, 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 of your drive. Maybe you have seen that in Windows, for example. And what this tool actually is doing, it is now in that case, for example, taking that and moving it up here so that we can use this memory down here again. This is what defragmentation is doing. Ta-da!
So how can we defragment?
Not at all.
Not at all.
Yeah, I mean, like we could, but the problem is now imagine like the applications for microcontrollers. Okay, and let's say, for example, your microcontroller is controlling your airbag, and you hit another car, and he's like, "Hold up, I first need to defragment my memory." Yeah, so very typically, embedded controllers are used for real-time applications. Okay, and it might be possible if you say, I do have a dedicated time slot in which the system is allowed to do this defragmentation. Okay, but typically you do not have such a thing, so it is just running, and you I was about to say you hope for the best. Not really. You test your system. You test your system extensively over time, okay, and also trace a little bit what is going on in the stack. Now, because maybe something we can, maybe also a question for the exam, what of course could also happen is that this application up here is never freeing that memory again. So it will require more memory and more memory and more memory. And at some point, there is no memory left. So, and this is what's called a memory leak. Okay. So what is a memory leak?
At some point there will be no heap memory left.
Okay, because?
Because the first memory allocation is not free.
Exactly. So if a function or a piece of your application is requesting memory all the time from the heap, but is not freeing it again, then at some point all the memory is used up, and this is what's called a memory leak. Okay, great. Very nice. Okay.
Can you please go over that again?
Okay. Maybe I'll do this with a small example. I could now in here that's stupid. That's stupid. Just trying to come up with a good idea. Let's say num1 is whatever this function is doing. Okay, it's just getting some user input. I don't know how, but I don't care. Yeah, so I get some integer number in here. Okay, and now I want to say, okay, maybe I need, for some reason, if the user said, for example, 5, I need to allocate 5 bytes. I need 5 bytes of memory. So the problem here is I do not know upfront how much memory I need. So for example, for SDHD, MATLAB could tell your microcontroller how many samples it awaits. Okay, so it is this point, once you know that MATLAB said, okay, I need, for example, 1,000 bytes, that you need to allocate this memory. Now you need the memory. Okay, is this already clear?
Yes.
Yeah, okay. So we now need suddenly in our application, let's say, this number of bytes. For that case, I'll just create a pointer. And in here, I can now say num1, for example. So what is malloc doing? Malloc, or its equivalent in C++ would be new, is allocating memory. Oh, okay. So what does this mean? Inside here, I say I need a certain number of bytes. So with that value, I specify how many bytes I need. Okay. Let's assume, for example, the user gave me 5. Yeah. So it will go to the heap. Yeah. So to this block here. So basically, this is representing the block down here. And say those 5 bytes are now reserved, okay? And malloc will return the first address of that memory block, yeah? So the address, the first address of this memory block is now stored in P memory. Okay, good. This is roughly understood?
The first address of the memory block. Well, how about the second address and the others till the 5th?
They are not returned because in the application now, I have to make sure that I have the number of bytes in here, okay? So I have to work with the first address plus the number of bytes I've allocated. And this, of course, again, is prone to error, okay? Because basically those two informations, they belong together. And if this information is lost, you're fucked, yeah? So this also might be a problem with dynamic memory allocation, yeah? You have to make sure that you do not exceed the memory you have been assigned, okay? Malloc, by the way, stands for memory allocation. I want this number of bytes, and it will return the pointer where it has found this memory. Okay? Not really, huh? You need to give me some feedback. It's fine if I repeat it 10 more times. That's fine.
No, it's
but
okay.
I need feedback. It's okay?
Yeah.
Now, at some point, typically, I would say something like free P memory. And what free would do is that it would simply say, I don't need this memory anymore. Okay? However, you might forget to do this. And then what might happen is basically, I mean, like you're allocating memory and it will never be freed. So maybe the next time you need more memory, then the user again gives us some data, we need more memory. And this will go on and on and on. And at some point, then there will be no more memory left. And this is what's called a memory leak. Now clear?
Yes.
Good. Good, good, good. Explain the polling and interrupt approach for data acquisition from peripherals.
Yeah, it was kind of theory question. It's like pulling always checking the request from.
I don't, and yeah, maybe what I also like now encountered when talking to you guys, you should always try, no matter if for an exam or especially later on for your thesis, you should always try to go to a so-called meta stage. Yeah, we're not in that topic, but we're a little bit above and describe what are the benefits of that. I do not want to know too much like what polling is, but I want to know about the characteristics or like what is the consequence of doing polling. I know this is difficult or more difficult. And I also had problems to get used to that. But this is like what is required. Like this is the scientific stuff. Yeah. So polling means that if we have down here, maybe we have something like a while 7 is also fine. While 1 loop, and in here we say whatever. Yeah. So, which means that this here basically is cyclically called over and over again. This is polling. The problem here is that do stuff might take a long time. So, and if you, for example, want to have a control loop, then maybe you want also to control whenever there is a new sample and not just catch it at some point. Yeah, do you want to have this a bit more predictable? However, this is easy to debug. Yeah. The complexity is a little less. Okay. So you can also write down some benefits of that here, but this is basically polling. Yeah. In your normal program flow, from time to time, you manually check for new values. Okay. Drawback here might be not so much for an ADC, but for others, there might be no new data, and then you simply use time for checking something which is not there. Yeah. Also, problem down here, it's not only might take a long time, but this time might also, what is the name for that? Jitter. So what is jitter? It's not always the same time, but sometimes a little faster, sometimes a little slower. And this difference, this time, delta t, this is called jitter. Yeah, so it's jittering. Okay?
So this was pooling.
This was polling.
Yeah.
This was polling. So this is polling. Now, interrupt could be something like ISR new ADC sample or a new UART char, which is only called if there is a new UART char. So what's the difference between those now?
I think polling is easy to set up.
So
yeah, it looks pretty straightforward. Compared to interrupt.
Yeah, but from an implication, this is now your engineer's point of view. Okay, unfortunately, this is not that important. Like, but from the system point of view, the system design point of view, what's the difference here?
For the interrupts, I think the interrupt handler service the device, while the polling, I think the CPU is in charge of servicing the device or the software, the program rather.
So this ISR is also executed by the CPU. So, but the difference here is that we manually check from time to time if there is data, even if there is no data. The advantage of the ISR is we immediately react on this event. And this is like important. This is immediate reaction. This is from time to time. Okay. Of course, now this interrupting the CPU might cause other problems, okay? Especially, for example, there are even attack scenarios called interrupt flood. So basically, you do something so that the ISR gets called all the time so that your main program doesn't have time to do anything because it spends all the time in the ISR. So this whole timing can become critical with interrupts. Okay.
So that means the polling is more faster?
Yes, and no, the ISR is more faster. Wait a second.
So what about the efficiency of both?
Well, the ISR is more efficient usually because, as I said, like if there is new data, and only if there is new data available, and that's one important thing. Only if there is new data available, this ISR will be called. Okay, for example, only if there is a new UART frame available. While this will be called every time, even if there is no new data available. But our application has to manually check all the time if there is new data available and has to deal with that. However, I mean, like, it's nice that we also can react fast on events. The drawback is we might corrupt the timing behavior of our application with interrupts. So also here, it depends a little bit on the application and what you try to achieve, if polling is the way to go or UART. No, UART, ISRs, interrupt. UART. Cool, not cool?
So we have to write 2 points here for this question. It's an immediate, for interrupt, it's an immediate reaction, and it's called the CPU gets interrupted on the new data available. So it's more efficient and process is speedy. Or in polling, it's a manual and continuous check, and it will continuous check for the new data. So it's not that efficient.
Yes. Well, as I said, like, it depends on the application. Yeah. Let's say, for example, for a UART, it might make sense to use interrupts because you know that only from time to time something is sent by UART, and so it's safe to use in ISR. For an ADC, you might have an application where you say like, I don't care, like, but if I'm in that particular function, then I want to call the ADC, and not all the time. So it depends a little bit on your application, which way to go. Yeah, but those are the possibilities you have.
Okay.
Woo. Well, guys, so general impression when I corrected this part of the exam. So many people, so many students had a lot of code with them. And then they didn't even know the basic syntax of C. So that was a little bit frustrating. I mean, like, I have not taken away too much points for that because I was focusing on the idea. So like how you try to solve that problem, but yeah. And by the way, like in the previous exam, we had 45 minutes and you had the possibility to write 1 hour. For the new exam, like from the beginning, we will have an entire hour. So wait a second, some student wrote me an email regarding. Okay. What? Like, I hope there is no personal information in that, but just a student wrote me an email, and this is the font. What? Okay.
Yeah, I think I've experienced that before.
Yeah. So is it a bug or?
I think you should just translate it.
Okay. Student tried to translate it and used the wrong character set or what?
I think she sent it normally, but when you received it, you got it that way.
Okay. So, but I just want to check that because I hope that she is not asking like how to attend our session here, because it's regarding the repetition exam. So please wait a second while I try to parse that into something human readable. Oh, come on. Please hold the line. Okay. I like to withdraw from the exam. Okay.
So this is an interrupt.
That's an interrupt. Exactly. And the interesting thing about this, like, you experience that stuff all the time in real life. Okay? That now was an interrupt. I could immediately react on that. Okay? I could directly answer that student, but you had to wait. So I was corrupting the timing behavior of our session here. Or what I could do, I could frequently check every 10 minutes if I do have new mail. And that would be polling. That way, maybe like our conversation is a bit more fluid, but very often I will check my email and there is no new email. Very good. So that's the difference. Okay. Good. So 1 hour of exam. Let's go through that again. Open that thing again. Okay. A device. So I have not decided on which system I want to use for the new exam, but I guess it will be something comparable. I knew that there are a few things in here which might have been a little tricky, so I try to take them away. But the overall concept will be the same, like as always, input, logic, output. Yeah, like almost every application. Yeah. Initialization, input, logic, output, and sometimes deinitialization. Always the same. Good.
Professor, it will be also on a system level like this, right?
It's very comparable, very
okay.
comparable.
With several peripherals, like here?
Yeah, but others.
Okay.
Simply another system.
Okay.
Another type of input, another type of output. But basically the same thing.
Okay.
At least that's the idea. This is like my homework for today or tomorrow to come up with some questions. So DC motor control. A device shall be able to drive a brushed DC motor with incremental encoder. So that's our device, that's our DC motor, and back here is the encoder. Everybody is familiar with those components, yes?
Yes.
The device, which is controlled by a microcontroller, so small PSOC or whatever in here, has a knob to set the desired speed of the motor, as well as a 7-segment display to indicate the number of full rotations or the current speed. A button allows to switch between the rotations and speed. Okay, so this is our application. The microcontroller software shall be implemented without operating system. Okay, the following software functions have been defined for this project. This function here is automatically executed every second. For the ADC, which is connected to the speed knob, there is a function ADC init, which starts the ADC module in free running mode. So what does free running mode mean? Well, it's like you had that in SDHD. You start the ADC once and it on its own will produce data all the time. It's free running. You don't need to say start convert and it will give you one result, but instead it's free running. It runs on its own all the time. After the ADC has been started, the user can acquire samples with ADC get, where the entire range of the data type is used to represent the knob position. Okay, so let's think about that one. We have an U16 type, and we want to use the entire range for our knob, which means if the knob is down here at max, what value could we read out of the ADC?
To the power of 16?
Yeah, yeah, for
max.
example. Yeah, okay. And then on the other side of the max?
0.
Exactly. So I mean, like this is, there's no definition here, and you do not would leave points for that because of course it depends on how you connect your potentiometer. But the idea is that one side is 0 and the other is 2 to the power of 16. Yeah, which side is which, I don't care here. Okay, good. Whenever new data is available, also an ISR ADC new sample is executed. Low pass filtering is done internally. So basically you could use ADC get for polling, or you can use this ISR. Okay, so that's it for the ADC part. We need to start the ADC once. We know that the entire range of the data type is used for the knob. And we can get this manually with get, or we can use the ISR. And we do not need to care about any noise on that signal. Okay, the 7-segment display is started with display init, and after it has been started, every time you call display write, the value you have given will be shown here on this display. Okay, so please give me an interrupt if you have a question. Otherwise, I have to poll for your questions after the text. See, once again, the same thing happening all the time. The mode button is configured by button init. After it had been configured, an ISR button pressed is executed every time the button is pressed. So we do not need to do debouncing. The function, there's a typo, button read returns if the button is currently pressed or not. Yeah. So again, we can decide if we want to use solely the ISR or if we manually also want to read if it is pressed or not. The motor driver handles the control of the motor as well as the decoding of the incremental encoder signal. The driver is initialized by motor init, and the target speed of the motor can be set by motor set speed, and then we can simply give the desired speed. The desired speed is in a value in the range of -10,000 to +10,000 RPM at the motor. The encoder value, so I mean like that one thing is our desired value or desired speed. The encoder value, like how many revolutions it already had, can be read with motor get encoder, where the return value represents quarter revolutions of the motor. Because very often what those encoders are doing is that per revolution you get something like 4 pulses. You typically don't get 1 pulse per revolution, but typically 4, 32, or even way more. I once saw 1024 pulses per revolution. Yeah, crazy. So but we need to do some math here to calculate that back to actual revolutions at the shaft of our motor. Good. So that's basically it for the software description. Now, the questions down here, maybe we'll start with the first one. Initialize all required modules. 5 points. And I can tell you, I think the maximum points I gave for this exercise was like 10. Okay, so how would we do that? Where would we do that? Initialize all required modules. First question, what are the required modules here?
ADC, display, button, and motor.
Exactly, all of them. So where do we need to initialize them?
I think in the main.
Exactly.
Before the while, yeah.
Yeah, up here, all right. So we need ADC init. Okay, we need button init. We need motor init. What else? Display init. Bam, 5 points. Yeah, and like, to be honest, this was a bit frustrating in the exam. Not with you guys, but in general, because I thought like, how easy can it be? Like, yeah. So 1, 2, 3, 4 functions to use here. Yeah. Okay. Is that clear? What I've done here?
So here, what we use in LED is like start LED. Instead of that, we are using init function.
What do you mean by LED?
We use like start ADC, and here we are using ADC init.
Yeah, so, because this is the function as it was specified in here. Like this start and stuff, this is something which is PSOC related, but if you work on other microcontrollers, those functions might have different names. You always have to refer to the API. So this is, for example, this collection of functions for the ADC is called the API, Application Programming Interface of the ADC. And you always have to check the API documentation and see which functions are available. Yeah? And they might have different names. So look into the text and only use the functions which are available in the text. Maybe I'll put something like a table somewhere so that you can look it up a little easier. Yeah, but always refer to those. Also, what I saw a couple of times in here, this is how you call a function. This is how you declare a function. This is not what we mean. This is how you call it. Yeah, so basic C syntax. Yeah. So you might want to check that again a little bit. because I mean, like, you had all the code with you, and I feel like a lot of students said like, hey, I do have all the code with me, so I do not need to learn programming. No, yeah, so you need to practice this a little bit. Okay, but this part was clear, yeah?
Yeah, the the declarations of these functions are in the .h files, right?
Yeah, exactly,
Okay. Yeah.
exactly. They are basically in here. So I actually implemented that to prove that the exam question is consistent. Yeah. So yeah, they come from here. Yeah, but this is out of your scope. You simply use all the functions which have been described up here. Those are the functions you work with. Okay. Good. Set the motor speed according to the knob position. Well, there are now two possibilities on how to do that. We could, for example, do that in the while one, or we could do that where? Every time there is a new sample available from the ADC. So where we want to do that?
In the ISR.
Okay, then let's do that maybe in the ISR. So what is the first thing we might want to do here in the ISR? So once again, yeah.
Read the ADC value with ADC
exactly,
get.
Exactly. So, and this is returning a uint16 type. Okay, so in our ISR, we can say uint16 type is our ADC value, or let's maybe call that knob position, because this is what it is. Okay, and we use ADC get to get it. Okay, now maybe it helps if we write down knob position goes from 0 to 2 to the power of 16, right? So now what we need to do is to do some scaling to scale it down to our desired motor speed. So we need to do, what do we need to do mathematically? Because the motor speed here, we need in 16 type for our target speed, and we want to have the target speed in a range of minus 10,000 to plus 10,000. So maybe let's already declare that variable. Whoops.
So it was 10,000 or just 10?
A second. What was the question?
It was minus 2 plus 10 or 10,000.
For what?
Oh, I got confused in values. It was 10 or 10,000.
10,000. 10,000. This goes from minus 10,000 to plus 10,000 RPM. So, how do we calculate that?
We can multiply the value by 20,000 divided by 2 to the power of 16.
Mm-hmm.
And then, yeah.
Okay.
Yeah.
So what was the equation here?
So ADC value times 20,000.
ADC value times, and now look That's the reason why I had those values here. Motor max is 10,000 and U in 16 max is this 2 to the power of 16. Yeah. So times 2 times motor max. Okay, yes.
Divided by the max 2 to the power of 16. Yeah.
So so times 20,000. Not position 2 to the power. I'm not sure. I'm not sure, but I also do not care here. Okay, it might be correct. It might be incorrect. We would have to do the math, but we need some equation to do the math here. Okay, and I think that should be clear to everybody, right? So what needs to be done here, or not?
Yeah.
Yeah. Okay. And once we have basically calculated from this 0 to 2 to the power of 16 up to our minus 10,000 to plus 10,000. The last thing we need to do here is to use this motor set speed and give it our new motor speed. That's it. Yeah? That's this part. Clear? Or not?
Can you just go through it again?
Which part?
Like from, okay, I think I get the first part, like from the second part.
Okay. So this ISR is fired because our ADC has a new value. Okay. This clear?
Yeah.
Okay. If we now read the ADC, we will get a value between 0 and 2 to the power of 16. Okay, which is representing the position of our knob. Is this clear?
Yes.
Okay. Now the problem is we need now to scale from this value range to this value range. Okay. So if we look at this picture again, then basically this is minus 10,000, this is plus 10,000, and this should be 0. Clear?
Yeah.
Yeah. So we need a little bit of math here, yeah. And if this is maybe not correct perfectly, I usually do not check that. So, but you need to do some math here. And once we do have our new speed, then we simply call the motor driver and give the new speed to it.
Okay.
Yeah? Because also up here, it was said that we can simply use the set speed to set our desired speed of the motor. Okay. Boom, half the points. Okay. Now comes the part which is a little bit more tricky. Calculate the RPM, or do we need to talk about motor speed, not position again? Otherwise, I will continue.
Yeah, but I didn't understand what exactly I have to write here. It means I understand that it's like from 0 to 3 to 767, then 65535 for minus 10, 0, and plus 10,000 speed.
You mean for this portion here?
Yeah.
Yeah, I, for example, what I did here in my solution is this. This was my equation. Yeah. Up to you guys. But as I said, I will not focus on math. This is not a math exam. I want to see that you somehow know that you have to work with the 10,000 and 2 to the power of 16, and you do some math with that. Yeah. I will not focus on that too much. I want to see you read ADC, you do some math, and you write it to the motor. That's what I wanted to see here.
Yeah, but I was stuck here, then I was not able to move forward.
Mm.
So, yeah.
Okay. So, but the idea here basically is like, if we now, once again, to a little bit on that meta stage, is to say we need a linkage of this knob to the motor speed, okay? And the approach, like how we did that now in software, is like whenever there is new data from this knob, we immediately calculate the speed of the motor from the knob position. And now this is basically a module of our system, because this is functioning independently of anything else. Yeah? I mean, like that entire functionality now lives in those 3 lines of code. Yeah? Get the current position of the knob, calculate the motor speed based on the knob position, and write the value down to the motor. So get knob position calculate RPM based on knob position, write desired RPM to motor driver. That's it. Now? Good.
Okay.
So next question, like this usually was meant as a filter for the 1.0. Calculate the RPM at the output of the gearbox and store the result in a global variable. Decide which data type is suitable and provide a reason for your choice as comment in the code. Okay, so we need a variable for the RPM of our motor. What data type should we use here?
Int.
Why?
It's positive and negative values both.
Okay, that's already good. What about the value range? What is the value range we expect?
Minus 10,000 to plus 10,000.
Exactly. So which data type could we use for that? Can we use an int 8?
Yeah. Yeah, and we can use int 16 as well. So.
No, but we can't use int 8 because int 8 is only going approximately to 127. This is not enough. But in int 16 is going to 32,000. Yeah, plus minus. So this is, oops, this is the data type we want to use for that. Oh. Let me check. Or you have it in your slides, I think. No, it's not in here. Then we say, I don't care. Like, let's say minus 32,000. Yeah, I don't need like the precise numbers here, but just rough stuff. Or even if you would have written like 2 to the power of 15, I would be happy. Okay, RPM motor. So that's this part. Okay, already 2 points. Great. Now we need the other 8. Calculate the RPM at the output of the gearbox and store the result in a global variable. So basically what is meant here is we need to calculate back from the encoder to the shaft speed. How could we do that? What is speed? What is speed?
Distance over time.
Very good. So, and what is distance in our case now? If we maybe look at this again, what is distance in terms of our motor here? It's the change in the encoder value. Okay, this is the number of revolutions. This is our distance. And our time, bingo, our ISR. That's why we do have this 1000 milliseconds tick here. Okay, so as I said, like this was originally meant like as the, you get a 1.0 question. No? So idea here is we can buffer the old encoder value. Then we get every second we check for the new encoder value, and then we can calculate the speed of that. Is that clear? No?
Yeah, not really.
Okay. So if you, for example, you're driving in your car, okay? And you do not have a speedo, but the only thing you have is like your kilometer count. Okay? So even if you do not have a speedo, but you say like, okay, I check how many kilometers I had now, and in 1 hour I will check again. And if I know that in 1 hour I have 50 more kilometers, then I know that my average speed in the meantime was 50 kilometers per hour.
Mm-hmm.
Yeah?
Mm-hmm.
And we can do the same thing here, because we do have an encoder here, which is giving us the revolutions the motor has made. And here we check every second how much this value changed. And based on that, we can calculate the actual speed of the motor, average speed, within 1 second.
So this void ISR tick for 100 milliseconds is just checking the speed, or?
Basically what this is meaning is that, where are we? That this ISR is executed every 1000 milliseconds. And we can use this as a time base.
Okay.
Yeah. So first thing we need, global variables. We need a buffer for the encoder value. And this is a int32 type. This is a int32 type because the encoder value comes as an int32 type. Okay? So what we can every second here is to say we have another int32 type, which is, let's say, position now, and this should be motor get encoder. Okay, so this is the position we have right now. Now we can say that the delta position basically is the position now minus the old position. Okay?
Okay.
Good. And our RPM motor now is this delta position times 60, because we're doing that once a second, right?
Yes.
So we want to have revolutions per minute. But as I said, the encoder gives us 4 pulses per revolution. So we have to divide that by encoder ratio. That's it. One thing, we need to update the last position. So after we've done position now. Yeah?
Okay, what I understand is here, the second last in RPM motor, we got the position now, and then we have to divide that position with the time.
Multiply it with the time, because this is movement per second and we want to have movement per minute.
Okay.
This is called every second and we want to have revolutions per minute.
Okay.
And this division now is because we get 4 pulses per revolution. So we need to divide it by 4 at some point. Yeah?
Professor, I don't really get this part. What I actually understand that this point is an interrupt for the time. That is like what I got. So then how, like we are trying to change to get the position of the motor.
So you don't get how this algorithm works?
Yeah.
Okay. I'll use this example with the car again, okay? Let's say this is position now is getting like, okay, we drove 50 kilometers, okay? Like this is now abstract, yeah? Then the delta position will be, for example, we drove 50 kilometers and the last position was we started with 0. So I know now that the speed my car is going is this delta position. In that case, now it will be per hour, let's say, yeah, that this function would be called every hour. And let's say we do not have an encoder with that. Yeah. So now we know if this function would be called every hour and the position now is 50 kilometers, the old position was 0. So we know that our car is going 50 kilometers per hour. This was extremely abstract, but is it better now or?
Yes, that's all.
Yeah, good. So wait a second, phone is ringing. Of course, if we are done with that, yeah, we need to say, okay, position now, this 50 kilometers now will be our last position. Okay, so because we need to memorize that. Let's say now in the next hour, this thing is called again. Now the position is 150 kilometers. The old position was 50. So we know that for this second part now, our speed was 100 kilometers per hour. Yeah, and this is basically how this works. It's the exact same thing, but just with motor revolutions. Yeah.
Yeah, sure.
Okay. Good. 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 Last question. Switch the display, and I mean, like also here, what
Professor,
I did. Yes.
I have a question regarding the previous task. The position that encoder, the position of the encoder is like an angel, or what is that?
No, the encoder gives you just an integer number, okay? And how such an encoder works is that it gives you pulses per revolution. And if you, for example, now read the number 4 out of that in this example, then this would mean that the shaft has done 1 revolution, because we do have a resolution of 4. If you have 8, then the shaft did 2 revolutions. Clear or not too clear?
Yes, clear.
Yeah.
Yeah.
I mean, like I can also, like if you see, oops. So this is such a thing. Yeah. And I hope you can see it. And here's the sensor and here's the wheel. Now this wheel turns, and now it works in such a way that it's not, it depends a little bit on the motor, but it's not giving like 1 pulse per revolution, but on that wheel are actually 4 contacts, like in that example here. Yeah. So 1 revolution here at that wheel would give you 4 pulses at the sensor. Yeah. And this is then how you would do the math to get back to like, or from that encoder value back to the position. Yeah? And of course, if we now are able to calculate a delta position over delta time, we get speed. Because speed, let's see. Oh, is it the right speed? Oh no, like we should search. Where is it? Delta movement over delta time, or delta angle over time, or whatever. Yeah, that would be omega. Good. So that's that stuff. Last question was, and here again, you might want to check that a little bit for every exam, basically you do. I ordered the questions in such a way that the difficult part was in between and not at the end. So it's always good practice to first read all the questions and then decide which are the ones you can easily implement. Yeah? Good. Though in this case, you would have a dependency. Okay. Switch the display between rotations and speed every time the mode button is pressed by passing the respective value to the display driver. Okay. So every time it is pressed, it should change. Okay. So we can, for example, use this ISR here to do the trick. But the thing is, we need actually to memorize what was the previous state. So we need some kind of variable to store if we are in that one mode or the other, right? Good.
Yes.
Yes.
So for example, we could say bool, use this claw to say like, okay, this is the variable in which we memorize. Okay, what's going on? And now here we can simply say if G, what was the name, display mode? If it is true, then we can say after whatever we want to do, whoops, it shall be false. And if it was not true, we will set it true. So with that small piece of code, I already implemented this toggle mechanism, right? Every time I press the button, the state of this variable will flip, right?
Okay, and we don't need to mention here RPM and...
Yeah, wait a second, that's the second step. The first thing, what I did here is basically I created an outline, which is like every time I press the button, it switches between this piece of code and this piece of code. This was the first thing I wanted to achieve. Okay, so now the question is, I want to switch between the rotations and speed every time. Okay, so which means if I'm in, let's say, for example, in this branch, what I want to do is to say display, what was it, right? Something like that.
Yes, display right.
So let's say then here it should be RPM motor. And in that other case, it should be get encoder. Was it just pure encoder value? Rotations and speed. Yeah. Now the only thing, rotations means that we also need to divide here by encoder ratio. Okay, that's it. That's the exam.
And why it is written, void display right is in 32 value?
Display right.
7 segment display.
Display right gets an int 32 value. So let's check. The GRPM is an int 16. So that fits. This is all right. And the motor encoder is giving us an int 32. So it fits. Yeah. Like what I realized after like also going through that and talking to you guys, this was a little bit too much for 1 hour. I mean, like if you would have had something like 2 or 3 hours, I think that would have been better. Okay, so I try also to optimize the exam a little bit in that direction. Yeah, so I observed that this was maybe a bit too much. Yeah, but what frustrated me on the other side was like that almost no students had like just basic stuff like that. And I mean like that was geschenkt. Yeah. Good. So, but this is clear approximately?
Yeah.
Yes. Do you want me to send the solution to you like that?
Yeah, would be helpful.
Yeah. So if you want to have that, please drop me an email so that I can simply answer that email and attach it.
Hey, Professor, can you just go up a bit? I need you to clarify. Not here, still go up. I think the first, not here, the first part when you started, yes.
Oh, this part or?
Yes, I need you to explain this part.
Those are the global variables. Those are the variables which are, for example, this GRPM motor, let's say, yeah? We're calculating this one in this ISR tick,
Okay.
but we also use it here in this ISR button pressed, yeah? Which means that it cannot be a local variable, because a local variable would only be visible within this function, but we need a global variable which can be assessed from multiple functions. Yeah.
Yeah, but how you did identified it before it will be a global variable?
Well, it was even set in the here and store the result in global variable.
Mm-hmm.
Yeah, but apart from that, the thing is, like, you have two characteristics. Wait a second. You have two cases typically in which you need global variables. Yeah? So one situation might be that you use a variable in multiple functions, okay, and you cannot really pass that as a parameter. So basically, they both need to access the same data, okay, and you cannot, yeah, you know what I mean. Like you need a possibility to share that. That could be one thing. Another thing could be you want to preserve information. I mean, like in here, we could also have used a static variable, but the idea is, or the general problem is, once we leave this function and then it is called again, we want to preserve the result of that variable. And only if we have global variables, the results are preserved, because those variables do not go away. So they do not start to exist. Local variables, they vanish once the function is over, but global variables, they remain, basically. No?
Okay.
Yeah. So for example, this display mode, of course, we want to remember what is the current display mode. No?
Yeah.
But I see a problem with that. What might be the problem with that? Every time the button is pressed, we write the display once.
So after every 1 second, we have to again display. Yeah.
It's basically showing us all display values all the time. But we can fix that. In here, we just toggle the variable. Has it really deleted? Oh. And there is no control Z. Okay. I can't remember the name. And this was basically get encoder, something like that. Yeah. Motor. Motor get encoder, and what was the name? GRPM motor. Yeah. And because this way now the display gets updated all the time while our system is running, and this display mode flag will change every time the button is pressed. No? Good. And this last position here, last position again, because we need to remember the last position to calculate our speed. So this is why we need a global variable here. Okay.
Yeah.
So for the exam preparation, how to continue. I will, wait a second, then already. I mean, like you see your names in here, so I will not put you BCC. So Raphael Owens, Sankit Mihare. I need to look you up, 1 second. Mihare, Sankit, and Shazep. Sie sind gar nicht hier im System. Studieren Sie hier überhaupt?
Natürlich.
Yep. And then let's make sure this is saved. And then this should be... just check if this is the correct file. Yeah. And okay, then I would propose the following. So I've just sent it, the exam to all of you. Go through that stuff again. Think about every question. Like if the question is clear to you, fine. If you still have questions or like something is not clear or you feel like, I know approximately why, but not really, then dig into that stuff again, okay? Check the code I have written here, okay? Try to understand what I'm doing and why I'm doing that. Rewatch the video if you do have questions about it. I think we talked about everything which is in here, okay? Then watch that video again. Maybe, like, I can stop here. Wait a second. Like, we don't need that on the video.